Hi, today I will talk to you about high utility item set mining. I will explain briefly the problem and what is the HUI-MINER and FHM algorithm, to find the high utility item sets in data. If you want to try the high utility item set mining or the algorithm I will describe in this video, you can have a look at the SPMF library or software you can find on the web if you search for SPMF. It will give you the code, the data sets, to do some experiment, to try it, to use it on your data, or also if you want to do research on this, you can start from this code to do your project. Okay, so first let me define what is the problem of high utility item set mining, why it is interesting, and then I will explain the algorithms. So in high utility item set mining, the input is a transaction database. A transaction database is a small database like a table, as you can see here. And in this table, what we call a transaction means a record. So here I use the example about shopping. Let's say you have a store and we have some item A, B, C, D, E. A could be for apple, B for bread, C for cake, D for dates, E for eggs, or other products like cheese, noodles, and so on. So then a transaction is a set of items bought by a customer. So here in my example, I have a small transaction database. The first transaction is A, B, C, D, E. A, for example, the customer buy apple, bread, cake, date, and eggs. The second transaction is ABE, so another customer buy apple, bread, and eggs, and so on. So in this example I talk about shopping, but this can be applied to many other types of data where you have some symbols, A, B, C, D. Instead of products in a store, it could be for example the location that some people visited in a city and so on. But for today we'll talk about shopping, to make it easy to understand. So if we want to find patterns in this kind of data, there's a very popular task called the frequent pattern mining. It was proposed by Agrawal. The goal is to find, for example, what the people buy many times together. So if the input is a transaction database and we need to set a parameter called the minimum support. So minimum support means the minimum frequency. So if we set to 1, means we want to find everything the people buy together at least one time. And the result, the output, will be the frequent item set. All the sets of items that appear at least this minimum support time, this threshold. So let me show you this with an example. Here I have the same database I showed you before. So in this database we have 4 transactions, and here we set the minimum support to 2. Means we want to find all the sets of items that have been bought at least twice together by the customer. So for example, we find that the set E, the item set E, appear 4 times. It is at least 2 or more. So it is a frequent item set. D and E appear 3 times. D and E, D and E, D and E. So also a frequent item set. So this is a very popular problem. There are many algorithms to solve this problem. So given a database, we set some parameter and we want to find the frequent patterns in this data, the frequent item sets. So how to solve this problem? I want to explain the main idea briefly before I talk to you about high utility item set mining. So the naive approach to solve this problem is to read the database to count the frequency of all the possible item sets, the sets of items. So for example, we have the item set A. We can count how many times. AB, AC, AD, AE, ABC, ABD, B, BC, ABCD, and so on. So there are so many possibilities. In general, if there are n items, let's say here we have 5 ABCD, there will be 2 to the power of n minus 1 possibilities, combinations, okay? So minus 1 because we removed the empty set. So 2 to the power of 5 minus 1 for ABCD will tell us there are 31 possibility, okay, if we remove the empty set. So if you have only 5 items in your database, it's not a big problem, okay, to count all these possibilities. But let's say you have a store with 1 million items like Amazon and so on, then 2 to the power of 1 million will be huge, okay? So we don't want to use the naive approach where we count all the possibilities. So to solve this problem, there have been many algorithms, efficient algorithms such as Apriori, FP growth, LCM, and so on. So the basic idea about all these algorithms, they use one very powerful property about the support, the frequency, okay? So I will explain to you how it works because it's important for later. So the a priori property, also called the antimonotonicity, is as follows. Let's say you have 2 sets of items, x and y. For example, x is AB, okay, and y is ABC. So we say x is a subset of y. So x could be AB, y could be ABC. Then the support, the frequency of y, must be less than or equal to the support of x. Okay, maybe not so clear. So let's look at an example together. Here AB appear 3 times in the database. Okay, AB, AB, AB. So what does it say, the property? Let's say x is AB. If you have a superset of AB, y, like ABC, ABC cannot appear more than 3 times. It can appear 3 times, 2 times, 1 time, or 0, okay? But actually this makes sense if you think about it, because if AB appear 3 times, you add something else like ABC, ABCD. It cannot appear more than AB, because AB is only 3 times. You cannot have ABC more than 3 times. So this property is very useful to design the efficient algorithm, because if you know AB appear 3 times and you want to find the item set appear 4 times, you know that everything that contains AB, you don't need to look at it, like ABC, you don't need to check, ABCD, BCDE, and so on, okay, ABCD, and so on. So this property is used by all the frequent item set mining algorithm to save time, to find the solution more quickly. So frequent item set mining has many applications, but it has also some important limitation. The limitation is many frequent patterns are not interesting actually. So even you find in a store many people buy bread and milk. Bread and milk still is not something so interesting maybe for the business, because bread and milk don't make a lot of money. Another limitation is we don't have the quantities of item. So either you buy like bread or you don't buy, but we don't know if you buy 5 bread or 10 breads and so on. And all items are considered as equally important. So if you buy 1 bread or you buy a computer, it is the same importance in this problem. But of course, if you buy a computer, it will make more money, more profit for the business than if you buy a bread. Okay. So let's continue. So to solve these issues, there's a new problem that has been proposed, okay, over the last decade, called high utility item set mining. It is a generalization of frequent pattern mining, more general. So the item can appear more than once in the transaction. So for example, you can buy 3 bottles of milk or 5 and so on. And the items have a unit profit. So we know the milk, for example, will yield a $1 profit. And the goal, instead of finding the frequent pattern, the goal is to find the patterns that have a high utility. High utility means high importance. It can be, for example, in terms of money. So we want to find the patterns make a lot of money. So using high utility item set mining, you could find some patterns, maybe like caviar and wine, some expensive products. Maybe this pattern is not bought by many people in a store, but it make a lot of money. So this kind of pattern you will not find with frequent item set mining maybe, but you could find with high utility item set mining. The pattern may be frequent or maybe not, but make a lot of money, okay, maybe more interesting for the business. So let me show you this, how it works with some example, the problem, okay, then I will show you the algorithms and so on. So in a high utility item set mining, the input is a transaction database with quantities. So here, for example, I have 4 transactions, T0 to T4. The first one say, I buy 1 apple, 5 bread, 1 cake, 3 bags of dates, and 1 egg. So we have 5 transactions like this. And also now we have something new. We have the unit profit table. So we know that 1 apple is $5, bread is $2, cake is $1 profit, 1 bag of date is $2, 1 egg is $3, and so on. Now the user needs to set a minimum utility threshold, a parameter, and the goal is to find all the high utility item set, the sets of items or products that have a utility, a profit, that is greater or equal to that minimum. Okay, so let me show you this with an example. Let's say I have the same database as input. I set the minimum utility to $25. So the goal is to find all the sets of products that the people buy together that make at least $25. Okay, so this is the solution, the result we want to find. There's only one solution in this kind of problem. Okay, but the goal is to find the solution quickly. So for example, we find that AC make $28. When people buy AC together, it make $28 totally in the database. So 28 is at least 25, so this is a high utility item set, and these others also. Okay, so why we want to find this? Because maybe we can do some promotion. If we know AC make a lot of money together, then we can sell them together or give a discount or do some marketing and so on. So these are some examples. So I did not explain how to calculate the money, so now I would like to give you more details about this, okay, before I show you some algorithms. So how to calculate the utility, the profit in my example? We'll take an example together. Okay, we will look at the item set A and E. A and E means you buy A and E together, apple and eggs, but they must be together. This is important. Okay, you cannot have apple or egg, they must be together. So to calculate the utility of A and E, we call U A and E. We look where A and E are purchased together. So in the first transaction we have A and E. So we have 1 apple. 1 apple is a $5, so 1 multiplied by 5. 1 egg, 1 multiplied by 3, so 1 multiplied by 3. 1 egg for $3. Okay. Now we look the other transaction. We have again A and E together. They must be together. So 2 apple for $5, okay, 2 multiplied by 5, and 2 multiplied by 3 for the eggs. 2 eggs for $3 each. So there are no other transactions that contain A and E together. So the sum of all of this will be the profit when the people buy A and E together, the utility of A and E, the item set A and E, $24. So this is how we calculate the money, okay, the utility. Now, why this problem is difficult, interesting for the researchers? Because the utility is not anti-monotonic. That means we don't have the Apriori property that I explained before, okay, in frequent item set mining. So let me show you this with an example. I will explain, okay. If you look at the utility of A for apple, it is $20. If you look at the superset of A, you add something to A, like AE, it can be more, like $24. But then if you look at another superset of A, like ABC, it can be less, like $16. So here, for the utility, if you have a set of items like A, you look the superset like AE or ABC, the money can be more or less. So we don't have the anti-monotonic property like in frequent item set mining. So why? If you have A, $20, you buy more things like A and E together. It can make more money because you buy more products together. But here, ABC, it makes less money. Why? It is because this is ABC together. Even though you buy more things together, there are less people that buy A, B, and C together. So this can decrease the money. So because of this, the utility is not anti-monotonic. We cannot use the frequent item set mining algorithm to solve the problem. We need to design some new algorithms. So today I will explain some to you. So there are several algorithms to solve the problem. Here I show a few of them. Today I will talk to you about HUI-MINER and FHM. They are two very popular algorithms, and also because they are easy, and there have been a lot of extension of these algorithms because they are easy to do the programming, and also they are easy to extend. So you can add many other constraints like the time and so on to these algorithms. So how they work? The key idea: we have the utility of the item set that is not anti-monotonic. So instead of this, they will use some upper bound on the utility that will respect the Apriori property, the anti-monotonicity property, and then this will help you to reduce the search, to eliminate some possibilities. So I will explain to you first what is an upper bound. Okay, like the TWU is used by almost all the algorithms. So before I explain the TWU, I need to introduce some concepts. What we call the transaction utility. I want to give you the definition. The transaction utility of a transaction will be the sum of all the profit in the transaction, all the utility. Okay, so if we have a transaction like T0, I want to find the transaction utility of T0. That means I will take the sum of all the profit in this transaction. If you buy everything, how much money it will make, okay, in T0. So it is easy to calculate. We call this TU, transaction utility of T0. It will be 1 apple for $5, 1 multiplied by 5. 5 bread for $2, 5 multiplied by 2. 1 cake for $1. 3 bags of dates for $2, and 1 egg for $3. So the utility, the transaction utility here is $25, okay, for T0. Now let me show you another example so you can see how to calculate again. Here I will take another transaction, T3. So we have 2 apples for $5, 6 cake for $1, and we have also 2 eggs for $3. So the transaction utility, if you buy everything in T3, will be $22. Okay, so this is a definition. Now I will explain to you how can we use this to have some upper bound on the utility, okay, and how is useful to design the good algorithm. So what we call the TWU of an item set, I need to give you the definition first. It will be the sum of the transaction utility that contain the item set. So let me explain this with the example. If we have A and E together, apple and eggs, we want to find the TWU of this. It will be the TU, the transaction utility, the sum of the transaction utility for the two transactions that contain A and E. So A and E appear in T0 and in T3. So we do the sum of all the money, all the utility in T0 and T3, the transaction utility. So it will be 25 plus 22 is $47. These values we calculated just before. Okay, so this will be an upper bound. Okay, so why it is useful to find this, I will explain to you. So there's a good property with the TWU. It is, if you find the TWU of an item set like AE, it is $47, you know that it will be always more than the utility of AE. The utility of AE is $24. So if you know the TWU of AE is 47, you know that the utility of AE, the money, cannot be more than 47. In fact, it is less. It is 24. Okay. So this is something good to know. Another useful property about this is that if you know that AE, the TWU is $47, you know that anything that you want to make with AE, like AEF, ACE, and so on, AE, any superset of AE, cannot also have more than $47, okay? Because A and E appear here, and the TWU is the sum of everything with AE, okay? So if you find $47, you take any superset of AE, like ACE, okay, or ABCE. Anything you take cannot be more than $47. So this will be a very useful property in high utility item set mining, because if you know AE is $47, the TWU, and you want to find the item set make at least $50, then you don't need to look any item set with AE, because they will never be able to make more than $47. So there are many algorithms based on the TWU. Some of them, for example, are two-phase and UP growth. So what they will do, they will work as follows. They will do two-phase. Okay, phase 1, they will find each item set that have a TWU that is more than the minimum utility using the TWU upper bound. So this will eliminate many possibilities. And in phase 2, they will read the database again to find the exact utility of the remaining item set found in the first phase. Then it will output the high utility item set. So this is the basic idea used by many algorithms. Okay. But there is a problem about this. It is high utility item set mining is still very expensive task in terms of time or memory, because the search space can be very, very big. So in this presentation, I will explain two algorithms, HUI-MINER and another algorithm called FHM. HUI-MINER was proposed in 2012. It is a few years ago, but it's still a very important algorithm because so many algorithms have extended HUI-MINER. And it is one of the fastest algorithms, not the fastest today, but still very easy to understand and do the programming. Okay. So to search for item set, it will do a depth first search. So what does it mean? It will start from the empty item set, like you buy nothing. Then it will look at Apple, like if you buy Apple. Then it will try to add some item to this, like AB, apple and bread. Then ABC, apple, bread and cake. Then ABCD, ABCDE, okay. Then after this, it will try other combination. After ABC, it will try ABD, ABDE, and so on. Then ABE also. Then AC, and then AD, and so on, okay. And then B, and so on. So it will do a depth first search to explore the different combination of items. And of course, we don't want to explore the whole search space, all the possibilities. So we'll use some upper bound in HUI-MINER. It will use some upper bound to eliminate some possibilities to find the result more quickly, the high utility item sets. So how does it work? Okay, I will explain to you the basic idea. So HUI-MINER first will read the database one time. So here we have the database on top. It will read the database to create a data structure called the utility list for each item. So the utility list of an item like D is a table that has 3 columns. Okay, the first one is the transaction, the second is called utility, and the third one is called remaining utility. I will explain to you what it means. So let's look what is this utility list, okay, for the item set D. So the first column will tell you all the transactions that contain D. So D appear in T0, T1 and T2. Okay, so here in the table we have a row for T0, T1 and T2. The second column will be the utility of D in this transaction. So here we have D in T0, 3 bags of dates, and each bag is a $2. So 3 multiplied by 2 means 6. Here we have 3 again, multiplied by 2 means 6. And in T2 we have 1 for D, multiplied by 2 means 2. So this is the utility, the second column. It will tell you the money about D in these transactions. Now there's a nice property about the utility list of D, about this table. If you do the sum of this column, it will give you the total money for D. So here 6 plus 6 plus 2 will tell you that D totally make $14 for the utility, the profit. And another column here is the remaining utility. That means how we calculate this. Okay, so if you look the transaction that contain D, it will be the utility of everything, all the items that appear after D. Okay, so here after D there's only E. There's some order here between the items, okay, like A, B, C, D. So we look, everything appear after D, and we find there is E. Okay, so here in the T0 we have 1 egg for $3. So the remaining utility will be 3. Here we have 1 egg for $3, so it will be 3. And here there are nothing after D, so it will be 0. So why we want to keep this information? Because we want to know if you extend D, like DE or DEF and others, we want to know how much money there is left in the transaction to make the larger item sets. Okay, so there is a very nice property, an upper bound actually. Okay, I will explain to you. If you do the sum of the 2 columns here, the utility and the remaining utility, it will give you some number like $20, and this will be an upper bound on the utility of all the extension of D. So if you make like an extension like D and something else after D, like DE, it cannot have more money than $20. Okay, so this is very useful, because if you search for item set that start with D, like DE or DEF and so on, you know that it cannot make more than $20. So if you want to find the patterns make at least $50, then you don't need to look at D or anything that starts with D. You will save a lot of time for the algorithm. Okay, so this is the basic data structure in HUI-MINER. First, HUI-MINER read the database and will make the utility list for all the single item like A, B, C, D, E. So then, after you have the utility list, like for A and D, for example, for all the single items, so here I show you for A and for D, HUI-MINER can do some join. So it will take A with D. It can combine them together to find the utility list of A and D together, the item set A and D. So if you have these 2 utility lists, you don't need to look at the database anymore. You can just take these two tables, do the join, and you will get a new utility list for A and D. And from this, you will find that the utility will be AD $18, 11 plus 7. You can find directly the utility of AD without having to calculate it by reading the database, to save a lot of time. So how do we do the join? I would like to explain to you in more details. So it is easy. If you want to make the table of A and D together from the table of A and from that of D, you find first the transactions that are the same, T0, T2, and T3, and here T0, T1, T2. T0 and T2 are the same here and here. So here we'll have T0 and T2 that contain A and D. So this is easy to calculate, okay? You only need to look at this table one time and you can find this. Now for the second column, it will be the sum. So here for T0 we have 5, here we have 6. So the money for A is a 5, the money for D is 6. So for A and D in T0 it will be the sum. It will be 11, 5 plus 6. Here we have 5 and 2, so it will be 5 plus 2, it will be 7. So 11 plus 7 will give you the total $18. So without even looking at the database again, by creating the utility list of AD, we can find directly the money of AD is 18. Now how to calculate the third column, the remaining utility? It is also easy. So what we will do, we'll take the minimum. So here we have 20, here we have 3. We take the minimum, it will be 3. Here we have 3 and 0. We take the minimum and we put 0. So this is how to calculate. So this is the basic idea about HUI-MINER, okay? It will start from the single item like A, B, C, D. It will build the utility list, and then to find the larger item set, it will combine the table like A and D together to make AD and so on. Then it will use the depth first search, and using the upper bound, the remaining utility, it will decide does it need to search more or not. So for example, for A and D, if I go back, we find the upper bound will be 18 plus 3. So anything that starts with AD cannot make more than $21. So using this upper bound, HUI-MINER can decide whether to continue to search like ADE or ADF and others, okay, extension. So this is how HUI-MINER will find the solution quickly, okay, for the problems. So HUI-MINER is a good algorithm because it's very easy to do the programming, and also for example, it was found to be more than 100 times faster than the previous best algorithm like UP-Growth before. But still, high utility item set mining is still very costly in terms of time and memory. So there are also some other algorithms that have been designed in recent years. So here I will talk to you about another algorithm called FHM. So it is an extension of HUI-MINER, so you can think about it as an improvement, okay? So the FHM algorithm was designed by making some observation. The observation is the main bottleneck, performance bottleneck in HUI-MINER is the join operation. The join operation can be very costly. That means when you combine two tables, two utility lists, to make a new utility list. So to do this, you need to scan the two tables and compare them to combine them, make the new table. But if the database is big and the item set appear in many transactions, this table can be very big and it will take a lot of time. So to make a faster algorithm, we want to reduce the number of joins operation. then this will save the time. So can we reduce the number of joins? How can we do this? So in FHM we use a very simple idea to reduce the number of join operation in HUI-MINER. So we use a new strategy or optimization called estimate utility co-occurrence pruning. So the idea is, when we start the algorithm, we will build a table like this. It is a triangular matrix actually, and in this table we will pre-calculate the TWU of all the pairs of items. So the TWU of A and B together is 25, A and C together is 55, A and D is 33. So this we pre-calculate before, okay? We read the database one time and we find the TWU of all the combination of two items. Then using this, when we search for item set, if we want to make a new item set like ABC, let's say we want to make ABC together, okay, then we can look at this table. A and B together is at most 25. So if we want to find the pattern at least 50, then we know we don't need to make ABC, because AB cannot be more than 25. Or we could look at AC together cannot be more than 55, or BC together cannot be more than 54. So for ABC together, we know it cannot be more than 25. So using this simple table, we only need to make one time. By reading the database one time, we can eliminate a lot of join in HUI-MINER. And this new algorithm with this idea is called FHM, okay? So this table here, if we want to do the programming, we can create this as a triangular matrix. We don't need to make a full table, only half of the table. Or we use some hash map, because maybe a lot of zero in this table, there could be a lot of zeros, okay? So we could use a map instead of making a full table. This will save some memory. So as I said before, when we do the search, we will use this to reduce the number of joins. So if we have a new item set X that contain two items I and G, like the item set is ABC, contain A and B. If we find that the TWU of I and G, like A and B, is less than minimum utility, then X is a low utility item set, it's not high utility, and we don't need to look all its extension. We don't need to do the join to build the table of ABC. So as I said, if you have ABC is X, you find AB is $25, is less than the minimum $50, then you don't need to look at ABC and everything that starts with ABC, like ABCD, ABCDE, and so on. So to compare these two algorithms, HUI-MINER and FHM, we did some experiment to show which one is faster and how much join we can avoid. So we use some common benchmark database, some about shopping and so on. Here you have some statistics about this database, like chain store is about shopping. It has more than 1 million transactions, 46,000 different products, and on average the people buy about 7 items. So we do some experiment in Java. We compare these two algorithms. So here I show you quickly some results just to show you the difference in terms of speed. So we have the minimum utility here on the x-axis for the 4 database. Okay, so let's look at this one here, the first database dataset. So here we change the minimum utility, the parameter, and we look at the time for the two algorithms. So when you decrease the minimum utility, it will take more time because there will be more high utility item set, and the algorithms will need to look at more possibilities. So we find here that HUI-MINER is much faster than FHM, is much faster than HUI-MINER. So here, for example, FHM take 300 seconds to find the result, but HUI-MINER take more than 3 times, about, more or less, about 800 seconds, okay, not exactly 3 times, almost. On other database like BMS, there's about a difference also very big, about maybe more than 5 times, okay, more or less, and so on, okay. So this shows that FHM, using some simple idea, can make the algorithm a lot faster to find the high utility item sets. So there are other databases here. For the database that are more dense, there's a lot of items appear together. The difference will be smaller. But in general, for the real database about shopping, there's a big difference. So FHM has the best performance on all the database. It is up to 6 times faster, except for the very dense database like chess. So how about the pruning, the number of join we can avoid? So how many join operations we can avoid using FHM? A large amount. So on database like retail, we can avoid building about 87% of the utility list. So we save a lot of time to build the tables. On BMS, 91% of the utility list we don't need to build. So we save a lot of time. Also, we look at the memory in this experiment. We find that the structure, the EUCS, the table in FHM, okay, to do the pruning, the possibilities, the search space, it does not take a lot of memory, about 10 megabytes, but for retail, because there are so many different items, it takes more, about 400 megabytes. But this is not so much for the computers that we have today. So if you want to try high utility item set mining, you can have a look at SPMF, the open source data mining library. It is a software implemented in Java. It gives you more than 200 algorithms for pattern mining, and it has a lot of algorithms for high utility item set mining. You can use it as a software. You can also find the code, and you can also integrate in other software, even written using other languages. And you have also all the data sets to do some experiment, to do some research if you want to make new algorithms and so on. If you want to find the SPMF software, you can search on the web. You will find the website easily. Then you can download and try it and so on. Also, if you want to know more about high utility item set mining, you can search for the survey paper about high utility item set mining. Here I will show you one, okay? So here's one survey for high utility item set mining that I wrote for a book. We have a book also on high utility item set mining, but if you want, you can look at the survey. It will give you a good overview of high utility item set mining. It will explain what I explained today, but also some other basic algorithm, okay? So you could have a look at this. It explains all the concept, what is high utility item set mining. And also it will give you the code about FHM, for example, and so on. So let me show you very briefly. This paper has a lot more picture, a lot more explanation, okay? So here we have the two-phase algorithm. I skipped. And we'll have the FHM algorithm that will be a little after. Okay, where is it? So here you have the explanation of the FHM algorithm. You have the definitions. We have some example with the tables, and also you will have the code. Also, you have all the code the explanation. So that's all for today. I hope you enjoyed this presentation. You can have a look at my website for more videos about other algorithms. So that's all. See you. Bye.